Alright guys, so this is the first of two videos that are going to be a part of the first assignment for after spring break. In this video we are going to be going through and sort of reminding ourselves about the two conic sections that we talked about before break, parabolas and ellipses. And this is largely going to be from your notes. I'm going to have additional problems that I'm going to attach with a separate sheet to the assignment. But largely right here, you've already taken notes on the parabola and the ellipse, and this is just going to be a video that reminds us about what we talked about. And the last video is going to be on that last type of conic section that we didn't quite get a chance to talk about, hyperbolas. So what is a conic section? Well, a conic section is a shape that we get by cutting a conic, which are these two cones placed end to end with a plane. And if we cut into one of the two cones with a plane that doesn't go through a cone, then we get the parabola shape, right? If our plane goes all the way through the cone, we say we get an ellipse. And if the plane cuts perpendicular to the cone, we can say that ellipse is a circle. If our plane cuts through the top cone and the bottom cone, we get what we call the hyperbola shape here. So right here, we're just going to go through and remind ourselves about the equations that define these conic sections on the xy axis. We need a little bit of vocabulary first. Right here we said that when we define the parabola as a shape, we use a locus definition. And the locus definition of the parabola is the set of all points that are equidistant from a line, the directrix, and a point not on that line, the focus, right? So right here we have our directrix, this line right here in green, and we have our focus, which is this point, and that's not on the line. And we can say that the parabola is going to be the collection of all points that are equidistant from the focus and the directrix, right? The vertex of our parabola is the point that minimizes that distance from the focus and from the directrix. We say that the focal length is the distance from the vertex to the focus, and that's this length right here, from the vertex to the focus. And right here, since we're saying that this distance goes from the vertex to the focus, we can think about this distance as being positive or negative depending on the orientation of our parabola, right? We would say that the directrix is, of course, going to be a length p away from the vertex in the opposite direction. In other words, these two lengths obviously are the same, and that's, of course, how we've defined our parabola. We say that the focal axis is the line through the vertex and the focus. We can also think about this as the axis of symmetry. And we say that the focal width is the width of the parabola through the focus, and that would be this length right here. And because this is a length that is not necessarily defined going from one point to another, we're going to say that this length is always positive, right? We said that a parabola as a conic section on the xy axis with vertex hk can be defined vertically with the equation x minus h squared equals 4p times y minus k, right? And horizontally as y minus k squared equals 4p times x minus h. Now, within this equation, we're seeing that focal width 4p, but within the equation that 4p can be positive or negative, and that's going to tell us whether the focal length p itself is positive or negative, and that's going to help us determine how we're orientated vertically and horizontally, right, when we're going from our vertex to our focus. So our two equations that we graphed, or we were looking to graph before break, we graphed our first one, A, and we didn't graph B. We'll go into that next. But just to sort of go back through this, immediately we can see that because it's the x expression that's being squared, we know that our parabola is going to open vertically, either up or down. And right here we can take the vertex, where we've got 2 being added to x, And so right here we know that the x value of our vertex is -2, and right here we don't have anything added or subtracted from y, and so we can say that the y value of our vertex is going to be 0, and that gives us our vertex right there as the ordered pair -2, 0. Now right here we can take that coefficient multiplying the y expression, which in this case is just y, and set it equal to 4p to determine the focal length. Right here, when we set 4p equal to -8, we get p equals -2, which means that we are going down to from our vertex to the focus. So right here, -2 is the length p, and that means we're going down to the focus, right? And that would mean that we're going backwards up to the directrix, right? So we can graph both of those pretty quickly. Now, after that, we've basically gone through and graphed the vertex, the focus, and the directrix. We can use the focal width, which we have within the equation right there, to get a quick graph of our parabola. So right here, from the focus, we're basically going to be going out 4 in either direction to give us that focal width of 8. And right here, with those 2 points and our vertex, we can go ahead and graph our parabola opening down around our focus like that. Now, for example B, since it's the y expression that's being squared, we can see that our parabola will open horizontally. Right here, we can similarly pull the vertex pretty quickly from the equation of the parabola. Right here, we can say that since we're adding 4 to x, we know the x value of the vertex is going to be -4, and since we're subtracting 1 from y, we know the y value of the vertex is going to be 1, so we've got a vertex of -4, 1 right there. And we can go ahead and get that focal length by taking the coefficient that we're multiplying the x expression by 6 and setting it equal to 4p. So right here we can say 4p equals 6, and that gives us a focal length of p equals 1.5. Now that's a positive 1.5, so that means that we're going to be going 1.5 horizontally in the positive direction to get our focus. And that will give us the focus as -2.51, right? So there's the ordered pair of the focus. Right here we can go that same 1.5 in the opposite direction to get our directrix. So if we go 1.5 in the negative direction, we will get our directrix as the line x equals -5.5. And right here we can take that focal width of 6 and get 2 points on our parabola to graph the parabola with the vertex. So right here we would go out 3 in both directions from the focus, and that will give us the focal width of 6 through the focus. And right here we can graph our parabola through those 2 points and the vertex looking something like this. All right, so on the attached sheet, we've got 2 questions for you to look at. I want you to sketch a graph of the parabola with the focus and the directrix. So right here, we're basically giving you the equation of a parabola as a conic section on the xy axis, and I want you to go ahead and graph that guy. And I want you to plot and give me the coordinates for the focus, and go ahead and plot the directrix, draw that directrix, and give us the equation for the line of the directrix. On the second problem, I'm asking you to look at the graph of the parabola as a conic on the xy axis with the given focus and directrix, and come up with an equation for that parabola as a conic section on the xy axis, right? So right here, you can see that this is opening horizontally, so we know it's going to be some y minus k squared equals 4p times x minus h, right? And we would basically want to pull the information that would allow us to fill in the k, h, and p values here for this equation. All right, guys, so I want you to pause the video here and take a look at these. All right, guys, so going through this first one, we are going to graph the parabola defined by the equation x minus 1 squared equals 4 times y plus 3. Immediately we can pull the vertex from the constants that we are adding and subtracting to x and y. And right here we have our vertex as 1, -3, so we plot that guy right there. And then we have our 4p as 4, so right here, solving for the focal length p, we get 1, and that means that we are going up 1 from the vertex to the focus, since our x expression is being squared, and we know this is going to be a vertically orientated parabola. So right here, that gives us the focus. Then we're going to go that same distance in the opposite direction to get the directrix, which will give us our directrix as y equals -4, our focus as 1, -2. And then right here, we can sort of take that focal length of 4 and basically get 2 points on the parabola on either side of the focus, and then our parabola will be drawn through those 2 points and the vertex. And that is the graph of our parabola. Okay, so this next one was a little bit trickier. We had to sort of use the information that our graph gave us to come up with the equation for the parabola. So right here, we've got a focus of -1, 1, and we've got a directrix of 2. Now what that gives us is the distance from the focus to the directrix through the vertex is going to 2p. And basically right here, I'm going to take that as a positive value. I'm going to say that we have the distance from the focus to the directrix as the absolute value of 2p, and we can sort of see on the xy axis that that's a length of 3. Now, because our parabola is opening negatively, we know that that p value is going to be negative, since that p value is the distance from the vertex to the focus. We know that we're sort of going backwards on the x-axis there. And so that tells us that our 2p is actually going to be a -3, which tells us that p is going to be -1.5. So if we go back 1.5 from our focus, we get our vertex as 0.51. And right here, we've got all the information we need. We can basically plug in the x and y value of our vertex into our equation as the h and the k. And then actually right here, we can say that our focal width is going to be 4 times our -1.5, giving us a -6. So this is the equation that will define that parabola. All right.